usually.
Also, I can answer any question by mail if someone wants to ask me something specific or even not so specific. But so feel free to write me. We'll be happy to have some feedback.
Very cool. Don't hesitate to copy paste your email address in the chat if you want.
Yeah, okay, I'll do this.
Okay, so I see that it's going.
We are back live, yeah.
Bastien, you tell me when the machine backup. It's still recording on machine, or?
Well, I hope so, I guess.
Okay. Yeah. Anyway, it always works on YouTube. So, checking time. Okay, so I guess we can resume now after a 2 minutes break. So for this second talk, we have Giovanni Peccati, also from Luxembourg University. We'll talk about Wiener chaos and the geometry of random fields. So okay, we are listening.
Yeah, so thank you very much for this opportunity. So thank you to Ivan for proposing to share this space. So my talk will be in full continuity and resonance with Ivan's presentation, and I will illustrate some applications of the techniques related to the spectral limit theorem and more generally to the Malevich-Stein techniques to problem arising in stochastic geometry and some specific model of stochastic geometry where a prominent role will be played by random variables that belong to what we call the Wiener chaos. So let me start with Wiener chaos. So actually, you have already seen Wiener chaos in Ivan's presentation because we have seen Hermite polynomials, and actually Wiener chaoses in plane and infinite dimensional setting a role which is analogous to the role of Hermite polynomials as this complete orthogonal system of polynomial for the one-dimensional Gaussian distribution. So I will express some of my results in terms of chaoses. So let me quickly recall you what Wiener chaoses are in general. So we start with the real Gaussian family, what we take to be separable. And so it's a collection of centered jointly Gaussian families indexed by some arbitrary set. And then the Wiener chaoses that I denote by CQ for Q equal to 0, 1, etc. of this Gaussian family capital X are defined as follows. So C0 is the real line. And then C1 is what we usually call the Gaussian Hilbert space generated by capital X. So this means that C1 is the vector space closed in L2, real vector space, which is generated by the coordinate of capital X. And then for every Q bigger or equal than 2, the Wiener chaos CQ is the vector space closed in L2, which is generated by random variables with the form HQ of Z, where HQ is the qth Hermite polynomial, and capital Z is a unit variance element of the first Wiener chaos. So now, for future reference, let me recall you some explicit Hermite polynomials. So the zeroth Hermite polynomial is just 1. The first Hermite polynomial's identity is the monomial x, and the second Hermite polynomial is x squared minus 1. Okay, we will see them appearing in our application, so let me just point out at least these definitions. Now, by using the properties of Hermite polynomials, in particular in terms of orthogonalities, it's quite easy to check that orthogonal Wiener chaoses of different orders are orthogonal in L2, meaning that if you take two random variables coming from different Wiener chaoses, then they will be non-correlated. And also, by using the property of Hermite polynomial of being a complete system of orthogonal polynomials for the one-dimensional Gaussian distribution, one can actually show that Wiener chaoses orthogonally decompose the space L2 sigma x of square integrable functionals of this arbitrary Gaussian family, meaning that every random variable capital F in this space can be written as an infinite series converging L2 of the projections on the Wiener chaoses. Okay, so, and if you take capital X to be a one-dimensional Gaussian random variable, you recover the Hermite polynomials. If you take it to be a two-dimensional Gaussian vector, then you recover bivariate Hermite polynomials, etc., etc. Now, behind the scenes of Ivan's talk, and actually this corresponds to one of the staples of this Malevich-Stein theory that was illustrated towards the end of the talk by Ivan, there are at least two central limit theorems that I proved some years ago, respectively with David Noilart and Cyprian Tudor, that tells us that if you consider sequences of random variables that live in a Wiener chaos, then these random variables have a very rigid asymptotic structure. Wiener chaoses have in general a very rigid asymptotic structure. And these theorems are the following. So they are kind of behind the scenes, both of our talks. And it tells you the following. So now fix some order q bigger or equal than 2, and consider a sequence of random variables that live in a fixed Wiener chaos of order q, and such that they have unit variance. Now, this theorem that I proved with David Noillard in 2005, and then we refer to as the fourth moment theorem, tells us actually that this sequence converges in distribution to a Gaussian 0,1 and 0,1 random variable capital Z, if and only if the fourth moment of Fn converges to the fourth moment of Z, which is equal to 3. And by using this machinery of Malevin calculus, one can actually prove an explicit bound that I wrote down here in total variation. Now, so this theorem is good news, not only because this is an interesting phenomenon, but also because within a Wiener chaos, one has powerful and flexible analytical and combinatorial tools that allow one to compute things, expressions of this type, so moments of this type. And in particular, so this makes this kind of theorem particularly amenable to application and to the kind of applications that I'm going to describe in the rest of my talk. Then some months after having proved this result with David Noillard, I proved another result, which is kind of a multi-dimensional version of this. So this was proved by Ciprian Tudor. And this result tells you the following. Now consider another unit various sequence, Hn, and assume that this sequence lives in another Wiener chaos. So it might be the same or a distant one. And then assume that the covariance between Fn and Hn converges to some number. So in particular, if Q is different from P, then this number rho will be 0. And this result that I proved with Ciprian is that now the vector Hnfn satisfies a joint central limit theorem towards this two-dimensional Gaussian distribution, if and only if separately each coordinate converges to the corresponding Gaussian random variable. So if and only if each coordinate verifies a one-dimensional central limit theorem. So this is another particularly useful result, because if you now want to study the fluctuations of a sequence of random variables that is given by a sum of elements of Wiener chaoses, then it is sufficient to study separately each element of the sum and then glue everything together by using this joint result without really worrying about strange asymptotic independencies at the limit that would kill a joint Gaussianity. So this does not happen. You automatically have a joint Gaussianity from component-wise central limit theorems. Okay, so this is some sort of behind the scenes, and my goal is to illustrate how this concept, this asymptotic structure of Wiener chaoses, and also the kind of hierarchy of regimes that was pointed out by Van in the framework of the spectral central limit theorem. It is these central limit theorems that corresponds to long memory, that correspond to the critical case, that correspond to the short memory Breuer-Meyer case, emerge quite naturally in a geometric context. So this is actually part of, so this is my second part. I will explain how to apply this kind of techniques to some specific examples coming from stochastic geometry. So we really focus on most of the time, I will focus on one specific example, which is the one that was introduced by Van, this Barish random wave model in dimension 2. But towards the end of my talk, I will show you that this kind of phenomena are part of a larger picture, much larger picture of geometric central limit theorems and non-central limit theorems that are connected with these techniques. But I really would like to go through explicitly to this model because it connects, I think, in a very nice way with the content of Ivan's talk. Okay. So let me continue. So my model of reference will be therefore the same very random wave model that was introduced by Ivan. So this is a model that comes from 77. I'm using basically the same notation as Ivan. I'm denoting this Gaussian field by capital B. So it's a collection of jointly Gaussian random variables indexed by R2. And from Ivan's talk, we have learned that this field is centered, and then the covariance of this field, there's an isotropic Gaussian field, there's an elementary Schoenberg representation, in the sense that it is given by J0, Bessel function of the first kind with index 0, computed in the Euclidean distance between x and y. And now, if you use one of the equivalent definitions of Bessel functions, you also have obtained immediately the Bochner representation that tells you that this function is actually the Fourier transform of a unit probability measure on the unit circle computed in the point x minus y. So you have for free both the Schoenberg and Bochner representation of this field. Now, one standard result in the study of Gaussian fields, which is a consequence of the theorem by Kolmogorov, I think, at the beginning, is that since the spectral measure of B is supported in a compact set, then this process has with probability 1 paths of class C infinity. So it's a very, very smooth Gaussian process, as opposed, for instance, to the fractional Brownian field that was discussed at a certain point in Ivan's presentation. Now, what I'm going to use in the following, and what will play a role in the following, is an alternate characterization of this field, capital B. And actually, this alternate representation explains what Ivan was already evoking, that is the central role that this field plays in several questions related to the geometry of the Gaussian field. Indeed, one can prove that B is also characterized as unique center Gaussian field on the plane that verifies two properties. The first property is that one of B isotropic, so we know this already. It has a distribution which is invariant with respect to rigid motions on the plane, but also with probability 1, capital B is an eigenfunction of the Laplace operator on the plane. That is, delta B of x is equal to B of x plus B of x is equal to 0. It is therefore an eigenfunction with eigenvalue minus 1. So why is it the case? So by somehow a direct computation, one can show that if you have a stationary field, a stationary Gaussian field. So this stationary Gaussian field verifies this equation with probability 1 if and only if its Bochner measure is supported on the unit circle. And now, if you also require the field to be isotropic, then then the measure has to be the uniform one. And this is basically the proof. Now, as also Ivan was saying, one has to think about this field as some sort of canonical or universal Gaussian Laplace eigenfunction on the plane. So the universal nature of this is that it appears as the local scaling limit in a number of models of Gaussian random fields on surfaces. So I will evoke toward the end that it appears that the local scaling limit of random spherical harmonics on the sphere, of arithmetic random waves, which is a model of Gaussian Laplace eigenfunction on the two torus, and also maybe most impressively, it appears that the local scaling limit in the model that is called monochromatic random wave model. So this is a model that is a sort of an approximate Gaussian Laplace eigenfunction model on Riemann surfaces, verifying some geometric properties. And so one can prove that for this model locally, all these random fields have a description which is independent of the geometry of the manifold, and can be fully described in terms of this Barry's random wave. So there is actually much more to the picture. There are conjectures that link this field to deterministic eigenfunctions, but I won't really go through this in this direction here. So now, when one wants to study a field, a Gaussian field, a random field, the geometry of a random field, what one typically does is to study, for instance, Excursion sets of level sets. If you take your favorite book about random fields, one central topic is the study of level sets. It is the subset of the domain in which the field takes some values, or excursion sets, the shape, the geometry of excursion sets. So what I'm going to do in this talk is to focus on one specific level set, which is called the Nodal set of Barry's random wave model. So the Nodal set is defined as follows: is B minus 1 of the singleton 0. It is the random subset of the plane where B of x is equal to 0. So for a random field such the Barry random wave model, which is a isotropic stationary field with a non-trivial gradient, so it is standard that the Nodal set is actually a smooth one-dimensional submanifold of R2. And you actually see in the picture on the right-hand side of my page a simulation of this that I stole from the webpage of Dmitry Belyayev in Oxford. So what you see here is a simulation of the excursion set of Barry random wave model. So the green domains, the green regions, are the regions where the process is strictly positive, and white ones are the regions where the process is strictly negative. And so, and the black lines between the green and the white areas are exactly the nodal the nodal set. As you can see from here, this is a collection of smooth, non-overlapping curves that are actually rectifiable in the sense that we can measure their length. And the length is the quantity I would like to focus on. So incidentally, let me also add that the nodal set of very random wave, actually the complement of it, which is called the nodal domains. So the complement of the nodal set is conjectured to be approximable by critical percolation models. So this is another fact that declares in some sense the centrality of this object. Now, in order to study the length and the structure of the distribution of the length, I will define B0 of t, so blackboard 0 of t to be the ball centered at the origin with radius t, and I will write L of t to indicate the length of the nodal set of various random wave model restricted to the ball B0 of t, and this is the same ball that appears here. And my aim is to study what happens to this length whenever I let the radius of this ball diverge to infinity. Okay, so this is a typical way of studying the fluctuations of the nature of the fluctuations of the given random object. You observe it on a domain, then you let the domain increase, and you see how by increasing the domains, what happens to the fluctuations of this random object. So my starting point is actually not a work of, starting point is not some result that belongs to me, but it is a paper from 2002 by Barry himself. So this is a paper, I put it here, the headline of the paper, and then some quotation, some citation here. So it's a paper in 2002 where, among many other models for Gaussian Laplace eigenfunction, Barry studied at least the first two moments of the quantity L of t that I just defined. So it is actually in the paper, the parameterization is different. So you won't find exactly what I'm going to tell you, but if you reparameterize things, then you will find exactly the facts and the statements that I will list in my notes right now. So what Barry observes in the 2002 paper is it observes that, okay, the expectation is equal to some constant multiplying t square, so it's commensurate to the volume, to the area of...
I'm sorry.
Yeah.
I'm sorry to interrupt you. Are you sure you didn't make typos in this? Because
No.
I believe it should be t, then log t, and
no.
I wrote to you on the chat.
No, there are no typos.
Okay.
And so the expectation is some constant t square, and then the variance of the length, which was computed by Barry, is given by, once again, t square multiplied by the logarithm of t, divided by 2056, which is a constant. And what Barry says in his talk, in his paper, is that actually, before completing the computation, he was expecting the variance not to be t squared logarithm of t, but to be t to the power 3. Okay, and so how is this done? Why these values appear in Barry's paper is that in order to compute the variances, Barry uses a tool which is an analytical device that's the Cast-Rice formula. So the Cast-Rice formula that I'm not stating here is a device that allows one to compute moments or higher moments like the variances of geometric quantities associated with Gaussian fields by expressing them as integrals involving conditional expectations. And these conditional expectations typically involve the field and the gradient of the field. And so what Barry does in this paper is that it approximates this conditional expectation by means of a series of oscillating and non-oscillating terms. And he observes here that the first non-oscillating term that should be the one that dictates the asymptotic for the variances was of the order, so here it was a lower order than the one that he was expecting because of some analytical exact cancellation of constants. And this phenomenon is described as an obscure phenomenon in the paper, so it's not obscure anymore. I will tell you why. And so this is what we call the Barry's cancellation phenomenon. And it's actually has been an observation, has been a remark that, the computation that has generated quite a number of contributions by several research groups. Now, if you are an attentive listener, then you see that all these regimes, T3, T square log T, and T square already appeared in Ivan's talk. And so this is not just this is not something that comes by chance. It's just that it is something that I would like to fully explain. And actually what I would like to do for the rest of my talk, I mean, for the main part of what is left in my talk, is to explain this Variance cancellation phenomenon by using Wiener chaos. So by using the concept of Wiener chaos, and more specifically by using the spectral central limit theorem that was described by Ivan. So by doing so, I will sort of rearrange and restate results that are contained in some papers, of which I am partially an author, written together with Ivan and Anna Vidotto, and then Anna Vidotto all alone, published from 2019 up to 2020. And so, but before going on, let me tell you that I'm not following a chronological order in the following sense. So after 2002, the cancellation of variance that was observed by Berry, the same phenomenon was rigorously confirmed by Igor Wigman in a paper of 2010 on the sphere for spherical harmonics. And then basically at the same time, it was also observed in a different form for arithmetic random waves on the torus. And the first paper that connected cancellation phenomena to Wiener chaos was a paper of 2016 that I wrote with Domenico Marinucci, Maurizio Rosso, and Igor Wigman. And then basically at the same time as our paper, there was a spherical version of this one. And between 2010 and 2016, there have been several papers where the terrain was prepared, in particular by Domenico and Igor Wigman on the concerning the model of spherical harmonics. But this is the one that, this model of planar random wave is the one that best connects to the talk by Ivan, to the phenomena described by Ivan. Okay, so now the thing is that in order to convince you and convince myself that the phenomena, that the spectral central limit theorem described by Ivan is relevant for the moment, actually explains this Variance cancellation phenomenon, one has to link in some sense the nodal length to Wiener chaos. So in particular, we have at least to be convinced of the fact that nodal lengths are square integral random variables that therefore can be developed in Wiener chaos, is right. So I'm going to do that in the next slide. So this is a sort of classical, albeit a bit technical computation that I will concentrate in one slide. So there will be a bit of hand waving, but not because the concepts are difficult or the techniques are transcendental, but simply because I don't know how to write it in a way which is not extremely boring for a Zoom presentation. So I will just compact things and hand wave a bit at a certain point. So the first thing is the following. So you can have a direct computation, but by direct computation, you can prove the following. If you fix a point X on the plane and you consider the vector given by the field, the first derivative of the field and the second derivative of the field, then this is a three-dimensional vector of center Gaussian random variables, respectively with variances 1, 1/2, and 1/2. So, and by the way, I will decorate sometimes gradients and derivative with a tilde, meaning that I'm multiplying them by the square root of 2 in order to make them a unit variance. Now, this fact alone, by a result which is known as the Bolinsky lemma, is enough to grant that with probability 1, 0 is not a critical value of Variance random wave model. So once you have this, you can apply what one calls the coarea formula and actually deduce that the length, which is the variable that we are interested in, can be obtained as the limit as epsilon goes to 0 of the following quantity is the integral over the ball of the grade of the Euclidean norm of the gradient multiplied by this approximation of the Dirac mass as 0, which is 1/2 epsilon multiplied by the indicator that the field in absolute value is less or equal than epsilon. Okay, so this is a Helmholtz limit. So with probability 1, this representation is true. Now, if you think about it a little bit, this random variable for fixed epsilon are square integrable because this is bounded. This is the Euclidean norm of a smooth Gaussian field with C infinity covariances, and this is a bounded domain. And with a bit of work, one can actually prove that as epsilon goes to 0, this is also a Cauchy sequence in L2, meaning in particular that LT by unicity is square integrable. And it is a limit in L2 and almost surely of this sequence for epsilon going to 0. Now, in order to obtain the Wiener chaos expansion, and this is the part where I hand wave a bit, one does the following. You fix X, and then you expand this red function into a series of univariate Hermite polynomials. then you can expand this blue function in a series of bivariate Hermite polynomials. So this will give you a sum here and the sum here. And then you bring the sums outside the integral and you let epsilon go to 0. And then you will have obtained a double sum of objects that involve Hermite polynomials of different orders. And on that, you will read the chaos expansion of your field. So this is basically independent of the fact that we are dealing with very random weight model. It's a very general procedure. So, but it's not important like to have all these details fixed or clear in your head. What is important is to understand basically what happens and then to be able to at least describe the first chaotic projections that arise from these procedures. And actually, the first chaotic projections are the following. So the first chaotic projection of the length of the second Wiener chaos is given by a multiple of integrals of what already appeared in Ivan-Stokes. That is the integral over the ball, 0t, of the second Hermite polynomial computed in the field. And then the same thing, the integral of the second Hermite polynomial computed in the normalized derivatives. Now, you can go on and make the following observation. So we know that C0, so the projection on C0 will be the expectation. This already was mentioned in Ivan-Stokes. And then something that I should have mentioned is that these two functions, the red one and the blue one, are actually even functions. And since Hermite polynomials of even order are even functions, of odd orders are odd functions, then this means that all Hermite polynomials of odd order will never appear in the chaos expansion of this variable, meaning that all chaotic projections of an odd order, 1, 3, 5, 7, will be equal to 0. Okay, so C2 is actually the first relevant projection. And then the second one will be the projection on the fourth chaos. And now the projection on the fourth chaos will also involve something that already was featured in Ivan-Stokes. That is, this projection will be given by 1/16, and then what we call the trispectrum, meaning this is the integral of the ball of the fourth Hermite polynomial computed in the field. And then some linear combination of integrals of trivariate Hermite polynomials of degree 4 computed in the field and in the two normalized derivatives. And if you go on with this procedure, so at the level 6, you will have a linear combination of integrals of polynomials, of Hermite polynomials in 3 variables of degree 6, then degree 8, degree 10, etc. Now, what I'm going to tell you is something that was already anticipated in Ivan-Stokes, is that all these projections encode one of the possible regimes that appear in the spectral limit theorem by Ivan when applied to Berry's random wave. And this is my next page, which is some facts. So it's a page where I list some facts. And these facts correspond to something that's already been discussed by Ivan, but somehow in this example come to life because it is something that arises naturally in the context of this computation of this model. And so in particular, so if you consider the summands that compose the projection on the second chaos, so this corresponds in Ivan's talk correspond to the case where the beta, so the beta is equal to 1/2, and this 1/2 is a value which is less than the ratio between D, which is the dimension of the underlying Euclidean space, and R, which is equal still to 2 because Hermite polynomials of degree 2 have, of course, Hermite rank equal to 2. So this corresponds in Ivan jargon to the long memory case showing Gaussian fluctuations. And if you remember the computation that was done by Ivan that I reproduced here, the variance in this case is equal to t to the power 3, which is the first value that was predicted by Berry in his paper before realizing that the value is actually different. Now you can go on and look at this trispectrum, which is a representative element of the fourth chaos. And this trispectrum is also part of what Ivan discussed. Here we are in the case where we have an Hermite rank of degree 4, of order 4. We have a dimension 2, and in this case, and beta is equal to 1/2, which is exactly equal to the ratio between D and R. And here is what Ivan referred to as the critical case. So this is the critical case that typically gives logarithmic type variances and Gaussian fluctuations. And so in particular, I reproduced here a computation that was already done by Ivan that tells us that the variance of this trispectrum at t goes to infinity is t squared log t, meaning that you have meaning that corresponding exactly to the kind of computation that Ivan did, and corresponding exactly to the exact order of the variance that was computed in Barry's contribution from 2002. Now there is something more. So there is a paper from 2020 by Anna Vidotto that extends some ideas in a work by Marinucci, Rossi, and Wigman for spherical harmonics that tells us that indeed, if you look at the fourth Wiener chaos, which is the trispectrum plus some linear combination of further integrals of trivariate Hermite polynomials, so this is actually fully correlated at the limit with so the whole projection of the fourth chaos is fully correlated to some multiple of the trispectrum. So actually understanding a fluctuation of this guy is the same as understanding the fluctuation of a multiple of this guy. So everything in the fourth chaos is explained by this trispectrum. And then we had another, I put here another fact that was proved in this paper with Ivan and Maurizia, that tells us that if you consider the projection of the length on all other Wiener chaoses of order strictly bigger than 4, that is 6, 8, etc., then this is negligible with respect to the variance, have a variance which is negligible with respect to the variance of the trispectrum, which was t squared logarithm of t. Actually, something more can be said, and was already said once again by Ivan in his talk, is that the representative element of a chaos of order bigger or equal to 6 is the integral over the ball of h to p b of x, where h to p is the polynomial of order 2p for some p bigger or equal than 3. And these guys verify a central limit theorem in the Breuer-Meyer regime, right? So they verify a central limit theorem in the Breuer-Meyer regime, meaning that the variance is equal to t squared. We have short memory, and we have a central limit theorem, which is absolutely analogous, even intuitively, heuristically, to the usual central limit theorem. Now, as a consequence, I can reformulate Barry cancellation phenomenon. And Barry cancellation phenomenon can be reformulated as follows. So now we have a sequence of random variables. This is the nodal length as t goes to infinity, such that the projection of the second chaos is composed of summands, with each one with variance t3, but the global variance of the length corresponds to the variance of the trispectrum, which is t squared logarithm of t. Okay, so if you wanted to put it even more schematically, this nodal length is composed of several layers of polynomials. The first layer is the second chaos, which has a variance t3 and corresponds to the long range regime. There is a critical case q equal to 4 that corresponds to the regime t squared logarithm of t, and then there is the short range regime corresponding to higher chaoses that have a variance t squared. And so in this sort of striking cancellation phenomenon tells us that even if we have a component that displays long range dependence and a variance of the order t3, what survives in this competition is the critical regime for q equal to 4. Okay, so this is the reformulation of the observation by Barry, completely in the language of the spectral limit theorem by Ivan. And now what happens is that, of course, there is some simplification in the second chaos that kills the terms in such a way that the variance becomes negligible with respect to the one in the fourth chaos. And the cancellation comes from the only piece of information about Barry's random wave model that I did not use until now. That is, that the field is, with probability 1, a solution, an eigenfunction of the Laplace operator. And actually, by using this, one can prove that the projection on the second chaos reduces to an integral over the boundary of the circle with radius t, where what we integrate on the boundary, so this is a one-dimensional Hausdorff measure, is given by the product of the field and of the inner product of the gradient with unit outward vector at the point x on the ball. And by using this and then combining it with Jensen and Cauchy-Schwarz, one can prove that this variance is actually bounded by the square of the perimeter of the ball, which is commensurate to t squared, of course, and which is negligible with respect to t squared log t. Naturally, one can push the computations a bit more and prove that this variance is of the order t. Okay, so not the area of the ball, but the perimeter of the ball, which is like another layer of variance regimes, which is hidden within this model. Now, a word about the proof of this cancellation is that, so we know that B solved this equation with probability 1, and now everything is an exercise in integration by parts, meaning that you can rewrite the projection on the second chaos as minus twice the square of the field plus the integral over the ball of the squared Euclidean norm of a normalized derivatives. Once you have written, so remember that the tilde means that I've just multiplied by the square root of 2. Now, when you are in this situation, now you can integrate by parts. So if you want to apply the first green identity, and then represent this integral as minus twice the integral of b multiplied by the Laplacian plus the same boundary term that appears in my statement. And once you are here, you can use the fact that delta bx is minus bx in such a way that this becomes exactly the term that simplifies with this, and the boundary terms stays. Okay, so the integration by parts is exact, and so reduces the projection on the second chaos on the just to a negligible term. So this is actually a clever idea that I wish I had myself, but it appears for the first time in Maurizio Rossi PhD dissertation in the spherical case, 2015. And then in a PhD dissertation of Massimo Notarnicola, which was my student, there is also a full discussion in many other situations. So it's some sort of a general phenomenon, this cancellation. And then at the end of the day, if we put everything together, so we have now shown that the projection on the second chaos that has potentially variance T3, but there's actually variance T disappears. And what you have at the end of the day is a theorem, which is the following central limit theorem. So the expectation and the variances of the nodal length are the ones that appear already in Barry's paper. And then by applying directly the spectral central limit theorem, one can deduce that properly centered or renormalized version of the nodal length converges in distribution to a Gaussian N01 random variable. So it verifies the central limit theorem, which is an amplification of what was done by Barry. Now, what one typically does is also to express things in a high energy version. And what I mean by that is the following. I can multiply the argument of Barry random wave model by the square root of E, where E is some positive number. Okay, so let me write it. E is some positive number. And this direct computation shows that this new field B of E is another eigenfunction of the Laplace operator, but now with eigenvalue minus E, right? Because you just take derivatives and see that it is the case. Now, what one typically does in order to compare, especially with other models of Gaussian random fields of manifolds, is to see what happens whenever your domain is fixed and the energy goes to infinity. So in view of this relation, the two things are completely equivalent. And if you do that, then you obtain that the expectation is commensurate to the area of D multiplied by the square root of E. The variance is the area multiplied by the logarithm of E. And then once again, you have a central limit theorem. Of course, you can express this random variable and this random variables, one in terms of the other. So it is just an exercise in renormalizing things and not forgetting about powers of E in the process. So this is just a complete reformulation of that. So to resume and to make some remarks about the central limit theorem, so it tells you at least one interesting things among all the phenomena that I pointed out. It tells you actually, answering the question that was asked in the first talk, that if one wants to extend the results described in Van Til, the spectral central limit theorem, to vector valued random fields, then this extension cannot be naively done. In the following sense, here I have exhibited the example of a function that has Hermite rank 2, such that each component of this vector, so it is a function that it is a function of a three-dimensional Gaussian field because there is the field and then the two derivatives. Each of the coordinates verifies the assumption of the spectral central limit theorem described by Ivan, but there is some algebraic analytical cancellation at the order of the second chaos, implying that the conclusion is not true. The conclusion that one would expect, that is that the second chaos dominates and the variance T3 is not true. Okay, so one has to be very careful when extending this to a vector value set. And then for the sake of curiosity, in higher dimensions, so in dimension D bigger than 3, it is actually, so if you consider the equivalent of Barry random wave model on Euclidean spaces for higher dimension, then all chaos is in that. So here everything will fall in the framework of the Breuer-Meyer central limit theorem. And every chaotic projection is expected to codominate, and the variance is expected to be of the order TD. So everything is expected because even if we expect this and we are quite sure that this is true, this requires a number of non-trivial technical computations, and some steps in this direction are contained in a paper from 2020 by Dalmau, Estrade, and Leon. Okay, so I think I still have 7-8 minutes, and so let me tell you that. So I want to just to give you an idea about the larger picture of what has been done here. So the larger picture is as follows. So first of all, by no means we are the first people to apply Wiener chaos techniques in order to study level and excursion sets of Gaussian fields. So there are a number of important papers by Slad, by Kratz and Leon, by Sodin and Zillerson, by Azais, Dalmau and Leon later on, that have used these techniques in several frameworks. So what is typically true, nonetheless, is that for the results by Slad and by Kratz and Leon to work, and for many derivatives of these results, one needs to have that the covariance function is sufficiently integrable. So for class L1 or L2 on the plane, which is not the case for the Barry's random waves covariance function, meaning that we cannot apply this result. And actually, what we do is really of a different nature, because we have all these different regimes that appear and one has to dominate. So this phenomena cannot be captured by the general results that are here. But the techniques, the idea of using Wiener chaos is this. Now, as I was telling you, so probably most of the progress in this area, that is application of Gaussian fields to study the excursion of geometric quantities of Gaussian fields, has been done on the sphere, right? This is a picture of the nodal domains for a model, which is the model of random spherical harmonics, which is a sort of the equivalent on the sphere of Barry's random wave model, where the equivalence comes from the fact that these are eigenfunctions of the Laplace operator on the sphere, but maybe most crucially, the covariance of this random spherical harmonics converges uniformly on very large regions in the high energy limit towards the covariance of Barry's random waves. So they're really linked. And heuristically, it is therefore not surprising, even if the proof is of course very, can be very demanding, that many of the phenomena that I described on the plane have a counterpart on the sphere. And actually, some of these results were proved before on the sphere before than on the plane. So for instance, between a paper of 2010 by Igor Wigman that detected cancellation in the variances, and then the full explanation with Wiener chaoses, which appears in a paper by Marinucci, Rossi, and Wigman, there has been a lot of preparatory works by Marinucci and Wigman, by Marinucci and Rossi, that basically pointed out phenomena of hierarchy of regimes between different orders of Hermite polynomial transformation that are similar to what I was describing. And then many cancellation phenomena have been discovered in this framework that are connected to what happens here. So there are works about critical points, and then about the intrinsic volume of excursion sets. And there are small-scale central limit theorems on the sphere that have been proved by Todino by using this small scales, means that we are looking at what happens when we restrict spherical harmonics to a spherical cup, and we let the radius of the cup go to 0 in some form. And then let me tell you that everything here is a very strong motivation that comes from the statistical analysis of cosmological data. So you can check the work by Domenico Marinucci about, and this is a picture of spherical cosmological data that correspond to the cosmic microwave background radiation. And what happens here is that the right way of taking limits is in the high energy limit, as I was telling the second part in the second formulation of our results. And here high energy has a very direct interpretation in terms of high resolution, so the detection of signals that comes from cosmological objects. Then there is another point, so I know I have 3 minutes, and I will try to stay within the limits. So now, what happens on the sphere is that the covariance function of spherical harmonics is uniformly approximable by the one of Barry random wave model, and this yields similar phenomena. Now, if you move to another context, which is the context of random field defined on tori, like the two-dimensional torus, here there is a simulation of nodal sets of some random function of the two-dimensional torus, then things are different, because the local convergence to Barry's random wave covariance function either does not happen or happens at a very, very small scales that are infinitely smaller than what happens on the sphere. And in particular, if you try to perform exactly the same program that I did on the plane, on the two torus, you will detect cancellation phenomena. The fourth chaos is going to dominate as on the plane, but the limit you will obtain is not a Gaussian one. It's actually a chi-square type limit that we discovered quite surprisingly in 2016. We were very surprised and puzzled by this kind of result. And there are small-scale limit theorems that have quite a different nature. And also something that breaks down on the torus is that if you go up with the dimension, whereas on the plane and on the sphere, you fall immediately within the Breuer-Meyer situation, which every chaos dominates. On the torus, fourth chaos continue to dominate even in high-dimensional settings, which is still a phenomenon that differentiates the two of them. And then we have also applied this kind of results to random monochromatic waves on general manifolds by some techniques of coupling. And there is a number of contributions that come from this direction, in particular, a collection of foundational papers by Kanzani and Anin from 2016 and 20. And then the even larger picture is about results that use techniques that are really very far from what I've described to you. And I put them here, so I won't comment on everyone. But for instance, a very natural question is to see what happens if one considers non-Gaussian waves. So there are quite a few results about that. And the general consensus seems to be that whereas expectation have a universal nature, it is independent of the distribution of the field. Second, on the results, even the order of the variance might change a lot according to the distribution of the field. So going from Gaussian to non-Gaussian is something that might create discrepancies with the Gaussian case. Now, something that is not part of my research activity, but I find it probably is even a larger and more ramified area, is about the study of non-local quantities. So the lengths that we deal with are local in the sense that you can measure the length of the nodal set on a small square and then glue many small squares and you obtain the global picture of, the global quantity, the global length. But you can do that, you cannot do this with non-local quantities. Like for instance, you can try to understand the number of connected components of the complement of the nodal set. Or you can ask yourself a question about the topology of this. And this can be done with there are several devices for doing this that are really have a non-trivial but quite limited intersection of what I described to you. And another kind of question is even far away in terms of techniques, even if the objects are very much connected, is about the percolative properties of the nodal domains associated with the Gaussian field. And in particular, let me point out, is a literature that increases by the week, more or less. And there is an extremely nice paper by Muirhead, Rivera, and Vanderbilt that studies this problem for the Barry random wave model. And this has been some sort of breakthrough because of the slow convergence of the covariance function. So there are more results in my notes that I will put online, and I will stop here by thanking you for your attention.
Well, thank you for your talk. So maybe some applause first. And now it's time for questions. So if you have some, feel free to ask them either by writing them or by unmuting yourself.
Can I ask a question which is not part of the main body? You said in the beginning, Giovanni.
Yeah.
So you said this striking result, which I didn't know, about the convergence of HN and FN, right?
Right. Yes. Let me. Right. Okay. The one. Right.
So I know this was not the central thing, but I was hooked on that. And why 2 and not 3? And can P be equal to Q? Questions like that. Can P be equal to Q?
Yeah. Yes. This is a multidimensional result that could go on for. I can take vector of any dimension. Right?
So I can have P1, P2, P3, and P2 for each thing, and then you get the same thing. So joint convergence, if and only if individual convergence.
Right, and the convergence of the covariance.
Yeah, and convergence of the covariance for any covariance.
For any covariance structure, and in particular, you can take things that leave Gaussian, vectors in Wiener chaos, vectors that whose components all come from the same Wiener chaos. And
right.
It works the same.
But there is no such, this is a naive question, there is no such result as saying, I don't know, a joint moment like expectation HN squared, FN squared or something converges, therefore it converges.
That's a good
fourth
question.
moment plus.
Yes. No, there is.
Okay.
Paper, is in a paper by Nodal and Nodal. Actually, what happens is that this is not the only thing. We can also, there is also a result which can be shown to be actually stronger than the fourth moment theorem, which is about the asymptotic independence of elements that live from the same inner chaos. It can be expressed in the covariance of the squares, and it's quite powerful. So
okay. So it's a totally stupid question. All right. Yeah, and the other thing is, I know that both Ivan and you mentioned that this field, what is called Berry's field, which I didn't know, appears as a kind of universal field for Gaussian fields on two-dimensional manifolds. So you mean that I can have something else other than a sphere and...
Yes. It is. So what happens is the following. So you can take a Gaussian field, which is defined on a two-dimensional manifold. Now, if you assume something about the geometry, global geometry of the manifold, like for instance, the negative curvature, something like that.
Yeah.
What happens in the following is that you have a model, which is acknowledged as a good model for random Laplace eigenfunction of this generic manifold. And you can build, starting from this model, you can build a Gaussian field on the tangent plane at any point. Tangent plane at any point. At any point, you can sort of project your field on a tangent plane by using the exponential map, and you obtain a new field which is known as the pullback monochromatic random wave. And this field, under absolutely very general assumptions, always converges locally to Berry's random wave, independently of the rest of the geometry of the manifold. Is a quite a striking result. But let me argue this. Actually, this is not the whole picture. The whole picture is that there is a conjecture by Berry that tells you that that I don't understand fully, so I don't like to discuss it during the talk. But it tells you basically that if you take a deterministic eigenfunction and you look at you let the energy go to infinity, then this deterministic eigenfunction looks like Berry's random wave model, independently of the geometry of the field, as soon as you have some sort of chaotic geodetic.
But the other thing is that this Berry's thing is isotropic, right? Or something.
Yeah, right.
So it is invariant under rigid body motions on the sphere.
Yeah, exactly.
So there must be some kind of condition like that for the generic manifold case. Otherwise,
yeah, you are right. The generic, this generic condition is somehow captured by, for instance, negative curvature. It's something a bit more specific. It's like absence of conjugate points. I mean, there are assumptions that exactly reproduce what you mean. This was the idea. You need something about the structure of the manifold in order to justify the isotropy. Exactly. This is captured by some conditions. So it's not general. It's not general. It's not.
Let me say something. I mean, I'm sorry. Just last thing. Okay. If you take Levy's Brownian motion, you know what that is on a Euclidean space, and you put it on a sphere, so you replace distance by geodesic on the sphere.
Right.
So that is isotropic with respect to rotations around the North Pole or something like that. Yeah. Can you not create a stationary thing by randomizing the North Pole, and then I will have a field which is non-smooth and something, something bothers me here.
I think I should think properly about it.
Yeah.
But it seems like a reasonable idea. And
yeah, that's so. I would start from something concrete that I know. This spherical,
this kind of Levy's thing or fractional things are really.
Okay, because the smoothness is what
exactly.
Amazing. Okay, this is okay. You're telling me that generically. Okay, nice. All right, thank you.
Oh, thank you for the comment.
Are there other questions?
Well, if I might, I have, so it's a very naive question. It's how robust is your theorem? Like, for example, if we replace the fact that B is an eigenvalue of the Laplace operator by F is approximately an eigenvalue, would it still work, or?
This is a question that I actually would like to consider. But so my expectation is that in this case, you will fall within the naive extension of the spectral limit theorem, in the sense that I would expect that the second chaos dominates.
Okay.
And then you have the variance like.
So it's very important to have exactly this equation to expect the cancellation of the.
Cancellation is exact, and even more so on the sphere or on the torus, because you have no boundary, right?
Okay. Yeah, I see.
Other questions, maybe? So I have one very naive one. so there is this phenomenon about the length of nodal lines, meaning like where the height is equal to 0. If instead of taking height equal to 0, we take height equal to 1 or something else, are there interesting things to say or not, or what's the situation?
Yeah, absolutely. No, this is absolutely true. So if you take if you just measure the length equal to 1, then you are going to approximate. I mean, in my procedure, we're going to approximate your direct mass with the direct mass is at 1. This approximation is not going to be symmetric. So you will have all the odd chaoses that pop up in the picture. And in particular, it might be that the first chaos dominates in this case. Now, and this, when we try to compute things exactly, it didn't work out perfectly well, but it is what we expect. On the other hand, you can also do an exercise which is a bit more maybe academic. That is, you can measure jointly the length of, let's say, level 1 and -1, so to obtain something symmetric. And in that case, I would expect once again that the second case dominates. So you have this variance T3 and things of the type. Modulo, I have to check the computations, but this is what I would expect. So yeah, it's really, that's all actually, so what, to answer jointly to the last two questions, this is not very robust in the sense that it's sufficient to move from level 0 to level epsilon to change the structure of the chaos expansion, and also to if you go from a Laplace eigenfunction to an almost Laplace eigenfunction, then things might change in some way. So yeah, so it's an exact phenomenon for this situation, but it's reproduced on many fronts. So it's general, but for eigenfunctions.
Yeah, it seems a bit like in statistical mechanics, there are sometimes these exactly solvable models where we have some algebraic stuff coming up exactly, and it seems to be a model which has this kind of miraculous rigidity compensation.
Right, but okay, but in any case, since we know that for those models of manifolds I was mentioning this, that are actually approximate Laplace eigenfunction, monochromatic random waves. So that they are approximately uniformly, in quite a strong sense, by very random wave model. And so even if these models are not isotropic, are not exact Laplace eigenfunctions, then the fluctuation of random waves propagates to them by a coupling or something like that. So it is even stronger. It applies to situations that are not at the beginning so perfectly miraculous, as you say, because of the universality. It is an object which is like Brownian motion. It appears universally at the end of many procedures that at the beginning do not have all the nice properties of Brownian motion. This is a bit the same.
Yeah, like the fact that random walk on Z2 seen from far, it's isotropic, not obvious a priori, but okay. So is there a last question, or if this is not the case, we can thank the speakers again.
Thank you.
And I will just finish by mentioning that the next seminar is in 2 weeks, and it will be given by Alessandra Caraceni and Alexandre Stauffer, and the topic will be edge flip Markov chains on triangulations on random planar maps.